this time we're going to take fractions and extend it to some things we've already done. We're going to be looking at order of operations and evaluating expressions. Let's look first at using fractions in order of operations calculations. Remember we had P, P, M, A, sort of some initials that I used to help remember the order of operations. First we deal with parentheses, then we deal with powers, exponents or roots. Then we deal with multiplication and division, and at the very last we deal with addition and subtraction. We've done some of this before, but now we're going to do it using fractions. Let's review a little bit just with some of the types of problems we've done before. Here we have 4 squared minus the quantity 2 times 3 times the quantity minus 4 plus 9. I've made the 2 times 3 and the minus 4 plus 9 slightly different colors so that you would understand that because those things are in parentheses, we're going to deal with those first. When I evaluate that then, inside the 2 times 3 I get the 6, so there's minus 6. Then in the second parenthesis, minus 4 plus 9 gives me 5. The next thing I need to do is deal with powers or exponents. 4 squared is 16. Next I deal with multiplication. 6 times 5 is 30. And finally I deal with addition or subtraction and am left with a value of 14 for that expression. This is just by way of review. Let's look at a similar kind of problem that contains fractions. It's really no different, except that now you need to use everything we've learned up to this point about fractions in order to do this order of operations calculation. We have 1/2 squared times the quantity 3/4 divided by 7/8 plus the square root of 45 over 5. Sometimes instead of seeing the square root over the whole thing, you'll see that little square root symbol in front of the quantity, and it means deal with the square root of the whole quantity. Let's take this step by step. The first thing we need to do is deal with what's in parentheses. Notice that the first thing I do, since I have a division, is invert and multiply. So instead of divided by 7/8, I use times the reciprocal of 7/8, 8/7. Then I perform that operation by looking at common factors. I have an 8 and a 4. I can divide both of those by 4, leaving me with a 2 where the 8 was, 8 divided by 4, and 4 divided by 4 leaves me with a 1. Next, I do that multiplication in the brackets. 3 times 2 is 6. 1 times 7 is 7. Okay, the next thing I need to do is deal with the exponents, the powers. I have 1/2 squared and the square root of 45 over 5, or 45/5. Remember that 1/2 squared is a half times a half, and in this case I could look at the square root of 45 over the square root of 5, but that's not going to give me perfect squares. But if I first divide or simplify, change 45/5 into a mixed numeral, in this case just 9, I can take the square root of 9. When I do these operations, I'm reduced now to 1/4 times 6/7 plus 3. Next I do the multiplication, 1/4 times 6/7. Working that out, I see I have a factor of 2 between the 4 on the denominator on the first factor and the 6 in the numerator on the second factor. Taking a mutual value of 2 out, I'm left with 1/2 times 3/7. That gives me 3/14 plus 3. That can be expressed as the mixed number 3 3/14. As you see, you need to take this just step by step and do it according to our schedule for the order of operations. Here's another one we can look at. We have 7/8 divided by 3 1/2 times 4/5. Before we can do anything else, we need to change that 3 1/2 to 7/2. Next, I have 7/8 divided by 7/2. Let me invert and multiply that, and that gives me, instead of divided by 7/2, I can use times the reciprocal, 2/7. I notice something right away here. I have a 7 on the top, a 7 on the bottom. Those will cancel each other out, giving me a 1 on each of those terms. You see, I can just get rid of both of those 7s. Next, I see I have a 2 and an 8 between the denominator of the first term and the numerator of the second. Dividing both of those by 2 gives me a 1 and a 4. Now when I work that out, this is what I have. Multiplying across, or I see something else. See that there's a 4 in a denominator and a 4 in a numerator? Those cancel each other out exactly as well. Almost missed that. It wouldn't have mattered. It would have come out in the wash, but I caught myself. You have to be observant when you do these things. And now what I'm left with is very, very straightforward, because multiplying across the top, I get 1. Multiplying across the bottom, I get 5. And my final result for this example is 1/5. Parentheses PPMA, parentheses, powers, exponents or roots, multiplication, division, addition, subtraction, the same as we've done before. The only difference here is we're doing it using what we've learned about fractions. We're going to do the same thing now and talk about evaluating expressions. Remember that an expression is just a mathematical description without an equal sign. You don't have an equation, it's only an expression. Well, you'll see. For example, we have x squared plus y, and if we don't know anything else, there's nothing we can do with it. But when we know the value for x and the value for y, we can calculate a numerical value for that expression. And what I do then is just plug in those values for x and y, do the math, and I'm finished. We're going to do this looking at fractions again. And in fact, we can do this in terms of a little word problem. And I would remind you again, we've used this before, that distance equals rate times time. Distance equals speed times time. Speed is a rate. And we'd like to find the distance of a Concorde flying at a cruising rate, or speed, of 1,336 miles per hour for 2 1/4 hours. Here is what we're looking for and what we're given as we've done before. Let's use it. We're given the formula distance equals rate times time, and we need to plug into that formula. When we do, we have 1,336 miles an hour times 2 1/4 hours. The first thing I need to do is change 2 1/4 to an improper fraction. There's something else I can do. Notice here that you can use units the same way you use algebraic quantities. I have hours on the bottom of miles per hour and hours up on the top of the 2 1/4 hours or 9/4 hours. Hours over hours cancels and leaves me with miles. I can use units actually as a way of checking whether what I'm doing is correct or not. First, I see I have 1,336 and a 4. Those, I can divide both of those by 4, giving me 334 up on the top left and a 1 down on the bottom right. Now I can do the math here, And notice that I've canceled out hours. As I said before, I have hours on the top, hours on the bottom, and the unit that's left is miles, which is what I'm looking for. How far have I gone if I'm going 1,336 miles an hour for 9/4 of an hour? What I'll be left with, the unit I'm looking for, is miles, and this works out. This type of thinking is actually used in science a lot. It's called dimensional analysis, and it's a very powerful tool for, first of all, checking to see whether you're correct. And even more deeply, you can actually help you to find the functional relationship of the things you're looking for. But that may be beyond the scope of this class. I just wanted to mention that using dimensions this way is an important part of science. Let's continue with the problem. I now have to multiply 334 miles times 9, and I am left with the fact that the plane will travel 3,006 miles in 9/4 hours. Here's one that I never even saw before. To make a right angle inside bend in sheet metal, I haven't had a lot of sheet metal experience, but this is a good example. The length of sheet metal used is given by the formula x plus y plus t over 2, where x is a length, y is another length, and then t is the thickness of that sheet of metal. Let's plug some values in. We'd like to find the length of sheet metal used when x is 6.5, y is 11.5 inches, and t is 1/4 of an inch. Now, to evaluate this, we need to plug those numbers in for their equivalent variable. And so we need to add 6.5 to 11.5 to 1/4 divided by 2. We, first of all, need to do the math for the 1/4 divided by 2. Let's get rid of that first. 1/4 divided by 2 is equivalent to 1/4 times the reciprocal of 2, which is 1/2, which is 1/8. The next thing I need to do is change all of those things, of course, to look at 6.5 plus 11.5. 6 plus 11 is 17. 1/2 plus 1/2 is 1. 2 halves is 1. 17 plus 1 is 18. Then I have that 1/8 left. My final answer for that is 18 1/8 inches. Notice that when you do a problem like this, you need to include the unit if a unit is given, if it's not just a pure number problem. Otherwise, if there are no units included, you may find that some of the credit is taken off when your work is graded. And if you are actually in business or industry and you handed someone a number, that could mislead them. For example, if I just said 385 for a length, would that be in inches? Would it be in centimeters? Who knows? It's very important to put those units in, be it just for a math class or for something important like a job or an engineering project. Let's now play with some geometry problems and use fractions for calculating areas. We have already played a lot with the areas of rectangles, and no matter which way the rectangle goes, the area is the length times the width. But a trapezoid is something like a pyramid or a triangle with the top shaved off, so in a way you have two bases. And a trapezoid, notice it's a four-sided figure, but only one pair of the sides is parallel. The other two could go any which way. And we can work our way towards the formula for a trapezoid this way. First of all, it's kind of hard to count square units for the trapezoid. That's going to be difficult, but we can play some games with it. Suppose we have this trapezoid where one of those parallel sides is x long, the other is y long. what I'm going to do is flip one of those, that second one over, and stick them side to side, this way. Here's a parallelogram. Suppose I cut a parallelogram down the side, and what do I have? I have what looks to be two trapezoids. I can start with the idea of the parallelogram because I know that there's the height of the parallelogram h, and the base of the parallelogram is x plus y. So the area of that whole parallelogram made up of the two trapezoids is base times the height. But since I've divided it in half, each half is a trapezoid, the area of the parallelogram is x plus y times h. Then the trapezoid, as I said, is a half of that. So the area of a trapezoid, if you think of it as being, that parallelogram as being made of two trapezoids, is going to be 1/2 of the area of that parallelogram, or x plus y, the sum of the two bases times the height divided by 2. I probably could have just given you the formula, but it's nice to know where things come from to get an idea. And again, you should probably write down the sum of the bases times the height times 1/2 or divided by 2 on your little card. Now let's look at an example. Suppose we have a height of 4 inches, and the long side is 8 inches, the short side is 6 inches. If we substitute that in, it's 1/2 the height times the sum of those two bases. Working that out, I get that the area is 28 square inches. Let's look at another one. Here we have two bases, 8 inches and 14 inches, and the height is 5 3/4 inch. Remembering the formula, the area is 1/2 the height times the sum of the two bases, 14 plus 8. When I work that out, that's 1/2 times 5 3/4 times 22, and I need to change the 5 3/4 to an improper fraction before I go any further. 5 times 4 is 20, plus 3 is 23. Now, if I can look through this and see if I can spot any common factors, well, I see there are some factors of 2 floating around. I can divide that 22 by a 2 and the 4 by a 2, and that looks about as far as I can go now. Multiplying across numerator and denominator gives me that area is equal to 253 over 4. Changing that to a mixed number, I find that the area of that trapezoid is 63 1/4 square inches. Now let's play with the area of a circle. We've talked a little bit about the geometry of a circle last time, where R is the radius, the distance from the center to the edge. The circumference, the distance around the circle, is 2 pi, that magic number that's about 22/7 times the radius. Let's play some games now. Suppose that we have this circle divided into 8 pieces, where each half is pi r, because remember the distance all the way around is 2 pi r. And I'm going to split those quarters out like that, those little segments of a circle. They almost look like orange slices. And then there are the ones from the bottom. I'm going to do a trick now. I'm going to shove those two sets of segments together, and look what I have. That looks an awful lot like a parallelogram whose base is pi r and whose height is r. What is the area of that equivalent parallelogram? Base times the height. That's pi r, the base, times r, the height. And so it looks like by fooling around and cutting that circle up into pieces, we've seen the area of that circle is pi r squared. Again, write this down. And now let's calculate the area of a circle with a radius of 7 inches. The area is pi r squared, and so pi is 22/7, or actually very close to it. R squared is 7 squared. We have 22/7 times 49 over 1, and I see that there is a common factor of 7 there. 7 times 7 is 49. Therefore, the area of that circle is 154 square inches. Now let's look at using polynomials that contain fraction and how we manipulate those. Remember that if you have two binomials multiplied together, we use the FOIL method. We have actually 4 different products here. We multiply the 2 first terms together, that's the f. We multiply the 2 outer terms together, that's the 2p squared and the 4, the o. The 2 inner terms, the ones that are closest together in the middle, the I, and then the 2 last terms together. We get 4 terms. There's the first, the outer, the inner, and the last. Then, of course, we need to clean these up quite a bit, and there's the first 2p squared times 3p. 2 times 3 is 6. P squared times p is p cubed. And then there's the second. 2 times 4 is 8p squared. The I term, minus 5 times 3p is minus 15p. And finally, the last product, minus 5 times 4 is 20. Let's do the same thing now with a couple of binomials that contain fractions. There's the first term, the outer term, the inner, and the last. Let's write these down. First, outer, inner, and last. Now we need to clean this up. Let's start here. We need to multiply 1/8 x times 3/8 x, and 1 times 3 is 3, 8 times 8 is 64, x times x is x squared. Next we have 1/8 times 5 times x, that gives me 5/8 x. Then we have 1 times 3/8 x, which gives me 3/8 x, and finally a 5. Now I notice I have 2 terms with x in that I need to combine. If I have 5/8 and 3/8, how many eighths is that? 5 plus 3 is 8. It's 8/8, and 8/8 is equal to 1. When I'm finally done then, I have 3/64 x squared plus 1x plus 5. Let's review now how we work with negative exponents. Remember that we can express 10 cubed as 1,000, 10 squared as 100, 10 times 1 is just 10, and remember that anything to the 0th power is equivalently 1. When we go in the other direction, we see 10 to the negative 1 is 1 over 10 to the first. 10 to the negative 2 is 1 over 10 squared. 10 to the negative 3 is 1 over 10 cubed, or 1/1000th, and so forth. Then, if we have 3 to the 5th over 3 squared, again we can divide that out and see that it's 3 cubed, or 3 to the 5 minus 2. Let's flip that around. Suppose we have 3 squared over 3 to the 5th. We can do the same thing. That gives us 1/27th, or 3 to the 2 minus 5, the same as we've done before, or 3 to the minus 3rd power. Or another way of looking at this is 1 over 3 to the third. Notice that, in a way, I have 3 to the minus third over 1 is equal to 1 over 3 to the third. If you change the sign of those exponents, what you're really doing is looking at the reciprocal of the terms. Very interesting and very, very useful. This is, let me read this carefully. A base with a negative exponent is equal to the reciprocal of the same thing with the positive exponent. I think I just said something like that. For example, 3 to the minus 3 is equivalent to 1/3 cubed. Then we can generalize it. X to the minus a is equal to the reciprocal with the a to the positive, 1 over x to the a. We can write this in the most general way this way. If we have x over y to the minus a, that's equivalent to y over x to the a. Let's look at a couple of specific examples. If I have 3/5 to the minus 2 power, I take the reciprocal, and that's equivalent to 5/3 to the plus 2 power, or 5 squared over 3 squared, or 25/9. If I have minus 3/5 to the minus 2 power, that's equivalent to minus 5/3 to the plus 2 power, or minus 5 squared over minus 3 squared, or again 25/9.